This is the introduction to Psy3233, Decision Making and Learning. The course has three parts. We start with what is the state of the world, which is making inferences about the outside world. More specifically, we'll be looking at Bayes' theorem, at signal detection theory, at ways to accumulate evidence, looking there at the sequential probability ratio test and drift diffusion models. Part 2 will be what do you want? So motivation, discrete actions and outcomes, effort sensitivity and reward sensitivity. So there the idea is that there is a discrete action that you can either do or not do. There's a discrete outcome that either occurs or doesn't occur. And your choice is just a binary choice, a yes-no choice, whether to perform the action, and then there is some probability that the outcome occurs. And then we'll be looking at how sensitive are you to the effort that takes, and how sensitive are you to the amount and probability of reward. There are also cases where actions and outcomes are continuous. So you may invest more or less time into berry picking. You may then get a smaller or larger amount of berries out of it. The marginal value theorem describes good decision making in such a context. We look at intrinsic motivation and possibly also incentive design. Finally, if you know what the state of the world is, you know how much you want a particular outcome, there is also what you actually do. How do you know what to do? And for that, we'll be looking at reinforcement learning. Franklin and Firkin suggested that every autonomous agent, including humans and other animals, spends its waking life in the moment-to-moment responding to the only question there is: what shall I do next? The idea there is that there are many things you may do, and out of all the options you've got, and based on what the state of the world is and what you actually want, you need to decide what is most worth doing. So that is a decision you have to make all the time. For making inferences about the outside world, we'll start by looking at Bayes' theorem, where the core concepts are priors, likelihoods, and odds. The principle is that if you imagine that a state of the world, a probability of something is happening, you can think of that as a number of cases that then divide into yes, this will be happening versus no, that will not be happening. And the idea behind Bayes' theorem is that then there is evidence that gives you some indication of which state of the world is actually the true state at the moment. And that evidence is described as a conditional probability, a likelihood. And what you want to do is you use the likelihood to find out how many states of the world are, or how many cases, given a state of the world, are compatible with the evidence that is available to you, and how many are not. And the ones that are not, you discard. You only focus on what fits the evidence. And that then leads to the idea that the product of prior odds and likelihoods, that's the posterior odds. You can generalize that to more than two alternatives, but still with nominal measurement, where you just have discrete categories, and all you know is this category is not the same as that category. You can also generalize to more than two alternatives and difference measurements. So there, it's not only that the different states of the world are ordered, but you also know this state of the world is that different to that other state of the world. And that leads us quite directly into applying Bayes' theorem to whole distributions. We'll look then at expected and unexpected uncertainty, or noise versus surprise. And I want you to give some thought to how you would represent ignorance. And finally, I would like you to think about how you would use Bayes' theorem to show why a scientific hypothesis should make precise predictions. The internet is reliably believed to be 80% cat content, so let's look at cats. So here is a cute kitty. What is the probability, or how likely is it that the cute kitty just wants scratches? And how can you express your initial or prior expectations as odds versus probabilities? And what is the difference? So let's start with odds. So, for example, imagine there are 8 cats and they distribute into 2 categories exactly according to the probabilities. So if you have 8 cats, we may have 5 that want scratches and 3 that don't. Or if we look not at 8 cats, but at 32, that would be a ratio of 20 to 12. And so we could, for example, say that out of every 32 cats, 20 want scratches. So 20 over 32 gives us a probability, but instead 20 to 12, those are the odds. Then we have the likelihood. So how likely is it that the cat is purring given that it wants scratches? So now we are only looking at the cats that want scratches. Out of the 32 cats, those were 20 cats. And now out of those 20, we want to know how many are purring. And here I have assumed that would be 16 out of 20, or expressed as odds, 16 to 4. Then here I allow only 2 alternative motivations for the cat. The cat either wants scratches or it wants to pounce on a tasty snack. And if the odds for one of the 2 mutually exclusive alternatives, and only 2 alternatives, is 20 to 12, then the odds for the other must be 12 to 20. So we have our 32 cats, 20 would like scratches, and 12 would like to pounce on a tasty snack. And then we have to ask, how likely is it that a cat that actually wants to pounce is also pairing? And here I've assumed that those are odds of 1 to 3 or 3 to 9. So out of the 12 cats that want to pounce on a tasty snack, 3 of them would be purring. We can display that as a bar graph, and there I would like you now to think about what would you do with that bar graph. So how do you apply likelihoods to this? And for that, I will stop sharing for a moment so that you can see this. So for that, I want you to use paper strips. And I'm serious about that. I want you to use paper strips and some scissors. And there are 2 reasons for that. One is that doing something with your hands, rather than just looking at something passively, makes it more memorable. Just in principle, because you have basically motoric encoding as well as visual. Also, it's a bit unusual to do something that primary school children do in the context of a university course. That also makes it more memorable. Plus, there is a 3rd reason, namely that this would be, or is intended to be, a reminder that what we're doing right at this moment is still very simple. And so we have then our odds. So here you can see we have 20 cases. So these are now the cats that want scratches. And we've said that the likelihood of pairing is then 0.8 or 16 to 4. So we have 20 cats. Out of the 20, 16 are purring and 4 of them are not. Oh, just a moment. So there are 4 of them that are not purring, and so that is now irrelevant. You have a cat that is purring. So out of the 20 that one scratches, you're not looking at one of those 4. You're looking at one of those 16. And so these 4 here are incompatible with the evidence you've got. So you crumple that up, throw it away. Then you do the same thing with this year. This year, these 12 cases represent the cats that want to pounce on a tasty snack. But we specifically have a cat that's purring. And so what's the likelihood of a cat purring? And we said that is expressed as odds, that would be 3 to 9. Expressed as a proportion, that would be 0.25. So a quarter of these cats are purring. That would be 3 cats that are purring down here, and 9 that are not. And so, because we're looking at cats that are purring, the ones that are not are irrelevant. You discard them. And that gives you the posterior odds. So the prior odds were 20 to 12. We've then multiplied each of these by the likelihoods. So that gives us 16 here and 3 here. So the posterior odds are now 16 to 3. And that is it. That's the basic idea. And I hope you agree that this is actually pretty simple. So what you do is keep the cases compatible with the evidence, and the likelihood tells you how many of those there are. So that is what I've done with the piece of paper. Oh, just a moment. Ah, I don't have a, do I have a pointer now? Sorry, just a moment. Ah, I don't have a pointer now. Well, anyway, so we have the bit that's crossed out. These are the pieces, the proportions that are incompatible with the evidence. So you don't need to worry about those because these are not the ones you're looking at. And so these are the ones you discard. And that then means that's what's left over is this here. And so that's where we've got that the prior odds multiplied by the likelihoods are the posterior odds. So the posterior odds are what you know once you have taken the evidence into account. And so you take the prior odds, that was 20 to 12. So you can write that separately like this. You multiply by the likelihoods. So we had the 0.8, or we can express it at 16 to 4. So we do that multiplication. For the 12, we multiply that by 0.25. So we can write that then as prior odds were 12 is to 12. The likelihood ratio is 0.8 to 0.25. And once we've done that multiplication, we get 16 to 3. And those are our posterior odds. So we had some initial knowledge about how likely it is that a cat wants scritches. Then we take additional evidence into account. The cat is purring. We need to know the likelihoods. So a cat that wants scritches, how likely is that to purr? So how good is that state of the world, a cat that wants scritches, at generating the evidence that is in front of us, the cat is purring. And it turns out that this is a high proportion. So a lot of the cats that want scritches are purring. Then we find that the cats that want to pounce are less likely to purr. So only a few of those do that. So this alternative state of the world, the cat wants to pounce, is not as good at generating the evidence that is in front of us. Therefore, a larger proportion of those 12 cases of cats that want to pounce has been discarded. And that then gives us this 16 to 3. So let's try that again. Here, we're looking at different evidence, crouching. And on Thursday, we'll talk about one thing there that I missed and I didn't have time to fix it. So I'll turn that into an exercise that is for you now to find out what is it that I didn't do quite right here. So anyway, I here assume that we have some prior odds again that the cat wants, hang on, that the cat wants scratches. But our evidence is now that the cat is crouching. So we're not looking at purring, we're looking at crouching. So we have the same initial odds again, we have 20 to 12, but the evidence is different. And let's assume that it's quite rare that a cat that wants to want scritches is actually crouching. So out of the 20 cats that want scritches, the 20 out of 32, only one of them is crouching. But then we have the odds of 20 to 12 in favor of wanting to pounce. And out of those 12 cats, basically all of them are crouching. Crouching before pouncing is a very cat thing to do. So I've assumed that that likelihood is 1. And so we can do the same thing again. So I'm looking here at 20 cats that are interested in scritches and 12 that want to pounce. But now our evidence is crouching. And we said that out of the 20 cats that want scritches, only one of them down at the bottom is crouching and the other ones are not. So this here all goes. And so I discard that. And throw away the ones incompatible with the evidence. Then I have to do the same thing with the others, only here I have nothing to throw away because all 12 of the cats that want to pounce actually are crouching. So now I need to share the screen again. So we have had this case here. We had the initial 20 to 12. Then 19 out of the 20 are incompatible with the evidence, so they're not crouching. So that gets discarded. And the 12 that want to pounce, all of them are crouching. And so our initial odds were 20 to 12. The likelihood ratio now is 0.05 to 1. If we make that multiplication, the posterior odds are 1 to 12. So we have 13 cats that are crouching, and out of the 13 cats, 12 want to pounce. So then we have this summary of Bayes' theory. Prior odds express your initial belief regarding how common the two alternatives are. You remove all the cases that are incompatible with the evidence. You do that by multiplying the relevant prior odds or prior probability, whichever way you express that. We'll get to the probability in a bit, with the relevant likelihood. And that tells you how many cases to keep. And the likelihoods are the probability of getting the evidence you see. So how good is each of the states of the world? In this case, what does a cat want to do? These are the two states of the world that we are taking into account. So how good are they at producing the evidence? And if you then phrase that question, for example, does Kitty want scratches? To get the true positives, you multiply the prior probability of the alternative that you focus on with the likelihood that this alternative would produce the evidence you see. And then you also have to, and so these true positives you keep, while the false positives you want to discard. So to get the false positives, multiply the prior probability of the other alternative. For example, does Kitty want to pounce on a tasty snack? With the likelihood that this other alternative would produce the evidence you see. And that gives you the two cases at the bottom, and that gives you then the posterior odds of 16 to 3. So we can do that also with other things. So here we have, again, the evidence is crouching, but now we're looking at something else that a cat may want. For example, does the cat want the toy, or does it want the cardboard box? And how likely is it that the cat will crouch, given that it wants a toy? And here I've set that to 0.75. How likely is it that the cat will crouch, given that it wants the cardboard box? And I set that as 1 in 24. And so that is now probability rather than odds. If we do the same thing again, so then out of here the initial numbers. So I have here one, oh, hang on. Yes. So the problem is that Zoom is in the way of what I'm actually trying to read, so I can't actually read everything that is on the slide. So the prior odds are 1 to 3 or 8 to 24. And so out of, again, 32 cats, we have 8 that want the toy and 24 we expect to want the cardboard box instead. So out of every 32 cats, it's 8 to 24. And so we have the 8 on the left and the 24 on the right. Then we apply the likelihoods to that. So we are asking if a cat wants a toy, how likely is it to crouch? And, well, quite likely. So out of those 8 cats, 6 of them are crouching, 2 of them are not. The 2 of them that are not crouching are crossed out. Those will be discarded. Then we look at the cats that actually want a cardboard box. So there are 24 of those, but only one of them is actually crouching when it sees the cardboard box. So again, we discard the cases that are incompatible with the evidence, and that leaves us then posterior odds of 6 to 1. So we started with 8 to 24. We multiply that by these probabilities of, or these proportions of 3/4 and 1/24. Then we can express that again as a likelihood ratio, 3/4 divided by 1/24, and that is equivalent to 18 to 1. And when we multiply the 8 to 24 with the 18 to 1, we end up with the posterior odds of 6 to 1. So for every 7 cats that are crouching, 6 of them want the toy, 1 of them wants the cardboard box. Then you can apply Bayes' theorem also to scientific papers, even if you do null hypothesis testing. So let's have a look at that. So what are the prior odds that a hypothesis is true? Now, in psychology, we're dealing with complex systems. Quite often we only have a vague idea of what they're doing, and the best we can say is, yeah, that hypothesis is fairly plausible. So we don't know as much as the physicists do, and therefore our prior odds of, for example, broken windows theory or the Oedipus complex are not actually that good. And so I have assumed that if you tested 50 hypotheses, maybe 10 of them would actually be correct. 10 of them would be true. So our initial odds are 1 to 4 or 10 to 40. Then what's the likelihood that a positive result comes from a hypothesis that is actually true? That would be statistical power, and we are supposed to do power calculations. And if we have some idea of what the sample size is, and we set our significance criterion, then we can determine the sample size that gives us the statistical power of 0.8 that we're supposed to aim for. And let's assume that we actually knew something about the effect size and that we could do a power calculation, that we have that statistical power. So that statistical power would be the likelihood of a positive result, given that you're actually looking at a true hypothesis. And the prior odds that the hypothesis is false, then of course would be 4 to 10, or 4 to 1 or 40 to 10. Then what's the likelihood that you get a positive result anyway, even though your hypothesis is false? And in social sciences, the conventional value for that is 0.05. Which is actually not a value chosen for good scientific reasons. I have read it was chosen for copyright reasons, because different statisticians had already made statistical tables for a false positive rate of 0.01. So then we test our 50 hypotheses. 10 of them are true hypotheses, 40 of them are false. We expect that our true positive rate is 0.8. So out of the 10 true hypotheses, 8 of them give us positive results. Then we look at the false positives. That's supposed to be 1 in 20. So if we have 4 false hypotheses that we are testing, then 2 of them should give us positive results, even though the hypotheses are false. So then the ones where we have negative results, we throw out. So we're looking only at positive results because I'm assuming now for the moment that we have gotten a positive results. So the negative results, these are not what we're looking at the moment. And so our prior odds were 1 to 4. Our likelihood ratio is 0.8, that statistical power we aimed at, divided by 0.05, which is the conventional significance level. And so what we would end up with is, in this case, that the posterior odds are 4 to 1. Note that this is not 1 minus the false positive rate. It's not 0.95. And we can go into that more deeply on Thursday. Now, let's generalize to more than 2 alternatives, but still nominal measurement. So, what if we're looking at more possible motivations? So, we now have 10%, or proportion of 0.1, of the cats we're looking at, they want scritches. 20%, or proportion of 0.2, they want to pounce. 60% want to sleep. And 10% want to lick their butts. You can see here the monarch of a jungle in typically regal posture on the left. And of course, then we need to look at the likelihoods. So for the 10% of cats who want scritches, there is 40% likelihood, or 0.4, that their tail is twitching. So twitching tail is what we're looking at the moment. That is the evidence that we have. Then for the cats that want to pounce, 90% of those twitch their tails. The cats that want to sleep, I've assumed that 20% of them twitch their tails. And cats that want to lick, I've assumed that it's also 20%. So how does that work again with our bar graphs? We need to give these bar graphs the appropriate heights, and that is, well, proportional to the initial probability. So here I have expressed that as a probability. We can also then just say that is, these are then odds of 10 to 20 to 60 to 10. Right? We have 10% wanting scritches, 20% wanting to pounce, 60% wanting to sleep, and once more 10% wanting to lick. Then these we multiply by the likelihoods. So we had 10 here on the left who wanted scritches, and 4 of them produced twitching tails, 6 of them don't. So that is the 10 divides into 4 and 6. Then we look at the ones who want to pounce. That was 20 out of those 100 cats. And because we have a likelihood of 0.9, that means that 18 of those cats would have twitching tails and 2 of them don't. When we look at the 60 cats who want to sleep, a few of those twitch their tails. I've assumed that proportion was, and now again I can't read it here, it's 0.2. And so the 60 then divide into the 12 that have a twitchy tail, So that is the 20%, and the 48 that don't have a twitching tail. So that's the rest. And then finally, the licking, that is 10 cats, again, 2 of them twitching tail, 8 of them not. So the prior odds were 10 to 20 to 60 to 10. The likelihoods 0.4, 0.9, 0.2, and 0.2. We do the multiplications. So 10 times 0.4 is 4, 20 times 0.9 is 18, 60 times 0.2 is 12, and 10 times 0.2 is 2. And so our, oops, what? That's 17, right. So we then go from prior odds of 10 to 20 to 60 to 10 to posterior odds of 4 to 18 to 12 to 2. If we want to turn those posterior odds into probabilities, well, these numbers now, the 0.04, 0.18, 0.12, and 0.02, if we express that as probabilities, they only add up to 0.36. So we should divide by 0.36, and that gives us the numbers on the left. So if we renormalize so that everything adds up to 1, that gives us the probabilities. And that is why we can also write Bayes' theorem in this form. So we're looking now at the probability that the world is in a particular state, state number I, given the evidence we have in front of us. And that is again this product of the prior, now it's a prior probability. So the prior probability of that state, state number I, multiplied by its likelihood. So the probability that this state of the world can produce, can generate the evidence we see. And that then needs to be normalized by all these products. That is what we've done down here when we went from the 4 and 18 and 12 and 2, and we renormalized that. So here, if we just do the multiplication, we could also call that 0.04. If we started with 1, 0.18, 0.12, 0.02, then we divide by the total, and then we get on the left our posterior probabilities. That is described by this equation. Right? So multiplying, so we had then these 4 steps. Just a moment. Again, I can't see everything that is on the slide. I have to check that elsewhere. So we had our prior probabilities. These express our initial belief regarding how common the alternatives are. We remove all the cases that are incompatible with the evidence. So these are the darker colors on the left. And we keep only those that are compatible with the evidence. And in the left diagram, that is the stuff at the bottom, the lighter colors. Once we've done that, we end up with what we've got on the right. So we've now gone to the posterior odds of 4, 18, 12, and 2. 4, 18, 12, and 2 adds up to 36. So if we divide by 36, then we end up with probabilities, like the ones we have here on the left. Now, I mentioned this is nominal measurement. So as long as we keep track of which category is which and which number goes with which category, it doesn't really matter in which order we put them. However, what if we have something that can be ordered and where we also know how different the cases are? And here I want you to imagine the following. I offer you a gamble. I've randomly chosen any number from 0 to 20. So I might do that by drawing lots out of a hat. That determines how many numbers on this 20-sided die are winning numbers. So that proportion ranging from 0 to 1 in steps of 0.05 is your probability of winning. What I would like you to think about is, if this is all the information you have, and you basically want, your task is to find out how many winning numbers are there. So that is your problem. And so what you should think about is, first, how many possible probabilities of winning are there, given how I determine how many winning numbers there are. What are the initial odds of each of these probabilities of winning? If you get to roll the die once, and you get it told only whether you would have won or lost, how does that change the distribution? And if you roll the die again, and again you get only told whether you've won or lost, you don't get told a number, how does that change the distribution? And finally, I would like to look at expected and unexpected uncertainty, or noise versus surprise. And that is the paper by Nasser et al., titled "An Approximately Bayesian Delta Rule Model Explains the Dynamics of Belief Updating in a Changing Environment." The task they give their participants is that they're supposed to guess the next number. They don't have to be accurate, but they get money in proportion to how close they get. And here I have assumed that the numbers that Nasser et al. Are giving their participants are, so those numbers range from 0 to 300. And here I have assumed that the distribution that generates these numbers is a Gaussian distribution with a mean of 120 and a standard deviation of 30. So 120 plus minus 30. And the winning strategy here is to work out the average of the distribution, and always to go for the average, because when you've got a Gaussian distribution, that is most common. So if you always go for the average, then that will get you pretty close most of the time. That basically would win you the most money in this gamble. But you don't know that the mean is 120 and the standard deviation is 30. You have to work that out from your experiences. And so here a number is randomly drawn from that distribution. And then, of course, at that moment, the best information you have is that is the mean. And that number here, but then, and at that point, when that is all you've got, your best bet is just to choose that as your prediction for the next time. Given that there are a total of 301 alternatives, it's not all that likely that you get exactly that number again, but you have a good chance of it being pretty close enough that you might earn something. By the time you get a second sample, you can get at least a rough idea of what the standard deviation might be. So the actual standard deviation is 30. And the actual mean is 120. But in this case, after you've had two samples, your best guess, based only on those two numbers, is that the mean is 126 and the standard deviation is 23.3. Then you draw a third number from that same distribution with mean 120 and standard deviation 30. But you don't know that it's 120 plus minus 30, and given on the three numbers, based on the three numbers you have experienced so far, your best guess is 107 plus minus 36. And so your best guess for the next number should be 107. In this case, what you actually got was 111. Oh, sorry. No, I don't actually remember now what the number was. It was a little bit above 120. And at that point, you would expect that the distribution, so your observation indicates a distribution with a mean of 111 and a standard deviation of 30.3. You do that a few more times, and in this case, I ended up with an estimate of 113 plus minus 25.1. So that's a bit off, but that is what happens when you've got a modest sample size. Now, the next one is out here. And at that point, you have to ask, does it come from the same distribution? Because there is an additional thing, namely that about once every 20 trials, so with a probability of 0.05, the distribution changes. You get a different mean. Sometimes you would also get a different standard deviation, but at the very least you will get a different mean. And that mean is picked at random from the 301 alternatives. It could, of course, be exactly the same mean as before. It could be so close that it's indistinguishable. But here in this case, you've got quite an outlier. So is that outlier evidence that the world has changed and that there's a new distribution, in which case you should ignore the old one? You should basically no longer use the numbers you have experienced before to predict the next one, because it's not merely useless, it's actively harmful, because the old mean is systematically wrong. You would always be far away the longer you retain that information. So at that point, if that outlier is good evidence that the world has changed, that there is a new mean, then you should discard the old information. And formally, what we're looking at is the number drawn here is 210. And so how likely is it that you get the 210 given that it was drawn from a uniform distribution with 301 alternatives, so that each of the 301 alternatives is equally likely? Well, that would be 0.0332, or 1 over 301. Now, what's the probability that the number 210 comes from the original Gaussian distribution? And there, I've deliberately chosen the 210 because it's 90 off from the actual mean. And so that would be 3 standard deviations. But of course, you don't know the actual mean, you don't know the actual standard deviation. So what you think you've got is 113 plus minus 25.1. Then you have to ask yourself, is that a significant enough outlier? And one way in which you can approach that is, how much better is the uniform distribution, where each of the 301 alternatives is equally likely? How much better is a uniform distribution at producing the number 210 than the Gaussian distribution? And so you can simply look up what is the value here versus what is the value here. So you look at this likelihood ratio, the odds of the uniform distribution being able to produce the observed data compared to the Gaussian. And it turns out that the uniform distribution is 364 times as good as that uniform distribution. that links into prediction error because you need to be able to distinguish normal variations from cases where the state of the world has changed. For example, if you had been living in Pompeii and you saw this here, this cloud coming out of Vesuvius, then maybe you should leave. But on the other hand, so you should leave so that you don't end up like this guy. But on the other hand, if you flee the city every time you see a slightly unusual cloud, then you will never get anything done. You may end up starving. So you really want to distinguish this state from the world from this state of the world. So that's the point. Each of these states of the world, either it's as usual or the volcano is erupting, produces, in this case, particular kind of cloud. And so they differ in how good they are at producing particular shapes of clouds. But when you have this likelihood ratio, which is 364 to 1, which sounds pretty impressive, what do you need to know in order to decide whether the world has changed? In this case, it would be just a different distribution. That is something that I would like you to think about so that you can work it out Thursday. And the task looks like this. You make an estimate. In this case, it would be 150. You then get the experience of the number that is actually drawn. Here it's 174, which is marked then in red. And the 150 are marked in blue. And then you get shown the difference, the error, in predicting the outcome. So how far off were you? And you can write that like this. So what's the probability of the outlier, the 210? If I just go back for a moment. So the last thing we have seen is this 210 here. That's the number that's been drawn. So how likely is it that you see 210 if the number was drawn from a uniform distribution versus how likely is it that you would see the 210 if it had been drawn from the normal distribution, but with a new mean? Now, I have made some figures of this probability of a change point, and we'll be discussing them in more detail then on Thursday.